we have introduced the loop method matrix form and the node method matrix form. This node method. Today we will introduce the cut set watch method matrix form, and then we will draw a conclusion for this chapter. The cut set watch method. This method uses the tree branch watch as a variable. Pay attention, the tree branch watch. For the loop method, we use the loop current as a variable. The loop current is also the core tree current. For the node method, the node method uses a node watch as a variable. The cut set method uses the tree branch watch as a variable. At first, we define the complicated branch also. For this standard complicated branch, we use admittance to express the branch with R. Admittance means we use voltage to express current. Use this UK to express this IK. For this branch, the UK plus USK will be this voltage. This USK plus this total UK will be the ZK voltage. So it multiplies the YK will be this IEK. This will be IEK. The total IK will equal to IEK minus ISK. So this just this expression. Y mod UB plus US. US means the source minus the IS. IS is a current source. So this is the admittance to express the branch VCR. Branch VCR means branch voltage current relation. For the KCL function, we use the QFIB equal to 0 to express KCL. The QF is the basic cut set matrix. The KVL is UB branch voltage equal to QF transform mod UT. UT means tree branch voltage as a variable. So QFIB is 0. Put this IB expression to this function. So QFYUB plus QFYUS minus QFIS equal to 0. And for the UB, use this function. So we get the QYQF transform UT equal to QFIS minus QFYUS. In this expression, the USIS is the source. The UT is a variable. The Q is a cut set function. So this function is very similar to the node voltage function. The node voltage function is A transform UN. Attention, this UN node voltage equal to AIS minus AYUS. So these two functions are very similar. Just replace the Q by A and the UT by UN. We define YT. This part use YT to express. We call YT the cut set admittance matrix. The diagonal line means the YT. This diagonal line. The diagonal line element is the cardset self-admittance. They are always positive. For other elements are the mutual admittance owned by two cardsets. This element. We define IT, the right side. We use IT to express. The IT means cardset current source vector. So we can write this function in simple form. YT multiple UT equal to IT. The UT is a variable. YT calculated from this expression. This YT. IT from the right side expression. Pay attention, the cardset method is the extended form of node voltage method. The node voltage method is a special case of the cardset method. If we choose a special cardset which make all the cardset branch connect to one node, then the cardset method will change to node voltage method. Steps for the cardset method. Step 1. Choose a tree. Write QYISUS. Step 2. Calculate the YT, IT, and get the cardset function YT, UT equal to IT. Calculate the YT, the UT, and then we can get the UB from the keyworld function UB equal to QF transform UT. When we finish the UB, we can calculate IB by KCL plus US minus IS. This then from the UB calculate the IB. For example, use the cardset method to solve this problem. Assume all the initial value is 0. This means these three components initial value 0 state. Draw the diagram. We choose the branch 1, 2, 3 as tree. Branch 1, 3, 2 as tree. 4 and 5 as a core tree. Then we can draw the QF. This cardset 1 means branch 1. Branch 1 cardset. The branch 1 cardset is a 154. And the tree 1, when this cardset, it removes the 145. The tree 1 flow from the part A to part B, and branch 5 also flow from the A to B part, so they are all positive. For the branch 2, the cardset 2, this cardset 2, this A part, this B part, 2 flow from A to B, but the branch 4 flow from B to A, so this position is negative. For the cardset 3, this A part, this B part, the branch 3 flow from A to B, and branch 4, 5 also flow from A to B, so they are all positive. So pay attention for the direction of cardset. The direction of cardset defines the positive or negative of these components. And this part will be uniform matrix. And the US and IS. The US, because this circuit has no voltage source, so you have 0. For the IS, pay attention. The branch 1 flow from up to down. The IS flow from down to up. And the branch 2 the same, up to down, this down to up. So these two current source direction is the same as we defined the basic complicated branch. So they are all positive. And then we draw the admittance matrix. Why admittance matrix? It will be a diagonal matrix. So when we get the Q, Y, U, S, I, S, then we draw the function. Q, Y, Q transform UT equal to QIS minus QYUS. And then calculate this part. This calculated from the QYQ transform. This UT. This part is QIS minus QYUS. So this is the cut-set method. And we have introduced the cut-set method is an extended form of the node watch method. And then sometimes the cut-set method will equal to the node watch method. For example, for this circuit, we choose 3, 5, 2 as tree. 3, 5, 2 as tree. We draw again. 3, 5, 2. This 1. This 1. This 4. This 1. So for this circuit, we assume this node 1. Sorry, this node 1. This node 2. This node 3. This node 3. For this circuit, we draw the Q. 2, 5, 3. So 5, 2, 3. We assume the 5 at first. 2, 3. Sorry. For this method, we can define any sequence 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the cut-set 1. This cut-set 1. The cut-set 1 is 1, 2, 5. 1 to 5, same direction. 1, 0. 1, 0. The 3, 0. And the 4 is 1. The 5 is 1. For the cut-set 2, will be 1, 0, minus 1, 0, 0. For the cut-set 3, will be minus 1, 0, 1, 0, 0. This is the Q. When we write the matrix A, insert the matrix A, this Q1, this Q2, this Q3, 1, 2, 3, 4, 5. For the node 1, for the node 1, the node 1 will be 1, 0, 0, 1, 1. The node 2 will be 0, 1, 0, minus 1, 0. For the node 3 will be minus 1, 0, 1, 0, 0. We can find they are equal. These two are equal. And we can define the UN node voltage is UN1, UN2, UN1, UN2, UN3. For the matrix A, we choose this node as reference. So the UT is U2 just U5, and U2, and U3 transform. We can find the U5 equal to UN1, the U2 equal to UN2, the U3 equal to UN3. So the total equal, the Q equal to A, the UN, the UT equal to UN. So these two functions Q, Y, Q transform UT equal to QIS minus QY, US will equal to the AYA transform UN equal to AIS minus AY, US. Okay, so for this case we can find the cancelled method is total the same with the node watch method. Total the same. So the cancelled method is an extended form of the node watch method. The node watch method is a special case of the cancelled method. So this is a conclusion for the relation between the Q and A method. Now we will make conclusion for this total chapter. For this chapter, and first, for this chapter M, the aim of this chapter, we try to use a uniform or standard method to write function for complicate circuit. And for this function, we will use computer to calculate this function. So the emphasis of this chapter is found a uniform or standard method. This emphasis of this chapter is standard method to write function. So the write function is the emphasis of this chapter. The emphasis is not calculate function. The calculate function we all use a computer. Actually, all the computer simulation software based on the method of this chapter. At first, this M, the method at first. We introduce turbulence, tree, and core tree. Core tree, and then we introduce the matrix A, matrix B, matrix Q. These three matrices to describe the topology. And also describe the KCL and KL. This is step 2. But step 3, we will try to describe this matrix form of the topology. The step 3 is a matrix form of the VCR. The matrix form of VCR. This is step 3. For the step 3, the matrix form of VCR matrix form. We define a standard complicated branch at first. Pay attention to the definition. This definition IK, USK, UK, this USK, this ISK. For this standard branch. Based on this standard branch, we use the Z matrix or the Y matrix to express the matrix form. For the Z matrix, is U equal to Z I plus IS minus US. For the Y matrix, is I equal to the Y U plus US minus IS. So for the VCR matrix form, we have two forms. Pay attention, these all are matrix. Then we finish the KCL, KVL with R, and now we arrive at the matrix form of sect function. The basic idea is KCL, KVL with R, add them together. We will add one more. For step 4, the KCL, KVL, KVL with a function. For the loop method, the KCL is B transform IL equal to I. For the KVL, B U equal to 0. The VCR is U equal to Z I plus IS minus US. Add them together. Sorry. The loop method, the node voltage method, and the capacitor method. The KCL, KVL, and the VCR, and the total function. For the loop common word method, the KCL is B transform IL equal to I, B. The KVL is B U equal to 0. The VCR is use the current express voltage U equal to Z I plus IS minus US. The total function is B transform IL equal to B US minus B Z IS. For the node voltage method, the KCL is AIB equal to 0. The KVL is AUN equal to UB. The VCR is I equal to Y U plus US minus IS. The total function is A transform UN equal to the AIS minus AY US. For the capacitor method, the KCL is QIB equal to 0. KVL is Q transform UT equal to UB. And the VCR is I equal to Y U plus US minus IS. Total function is Q transform and the UT equal to QIS minus QYUS. QoS. So these are the conclusion for these three method matrix form. Method matrix form: loop current method, node voltage method, and the cut set voltage method. This page explains how they come from and how to write the last function for the step 5. For a common circuit, how to solve the circuit? It will be very simple. At first, you should write the B or A or Q matrix. Write one of the matrix is okay, is enough. And then write the Z or the Y matrix. And then write the US or write the IS. So for any method, we should write the 2 matrix and 2 vector. 2 matrix, 2 vector. 2 matrix, 2 vector. And then at last, write the function. Pay attention, don't need to calculate, because this method designed for computer, not designed for human hand calculation. This method designed for the very complicated circuit and for computer to calculation. This is the total content of this chapter. Okay, this is the end of this chapter. Now we will introduce the chapter 3, two-port network. For the two-port network, I think most of you should have learned it in your undergraduate course. We introduce this part again because we will learn the multi-port network in the next chapter. So we will review this chapter at first, but will be fast. Pay attention. So this chapter will be fast for us. The function and parameter of the two-port network, the equal circuit of the two-port networks, and the interconnection of networks. Introduction. In practice, the two-port network was widely used in power transfer and signal processing. For example, this amplifier, operational amplifier circuit, we can treat the left side as the input, the right side as output, and this feedback network. This common filter, input, output. The transistor, the input small signal, the output large signal, and the transmission line. Maybe you are saying it's very simple, but actually the transmission line is very complicated because it's a distributed circuit. For the transformer, the basic transformer is also a two-port network. At first, we'll introduce one-port network. What's one-port network? The port what consists of two terminals, terminal 1, terminal 2, and the current flow into one terminal will equal to the current flow out of the other terminal. The I1 flow in must flow out, because they must conform to the KCL. This kind of flow in, it must flow out, or the KCL will be break. So for the one-port network, these two current will equal automatically. For the two-port network, a two-port network is an electrical network with two separate ports for input and output. We treat the left side as input, right side as output, and we assume for the two-port network, the left side I1 flow in will flow out equal. The I2 flow in will flow out equal. This is two-port network. But for common four-terminal network, for example, if this I1 flow in, but the flow out not equal to the I1, this I1, I2, I3, I4, we only know the I1 plus I2 plus I3 plus I4 equal to 0. This is the KCL. But the I1 not equal to the minus I2, and I3 not equal to the minus I4. So this will be the common four-terminal network. Two-port network. The two-port network is a special case of the four-terminal network. Special case of four-terminal network. So only when the four-terminal network, one terminal cannot flow in and will flow out from the other terminal, we can call it the two-port network. So there's a difference between the two-port network and the common four-terminal network. If there are connections out of the two-port network, it will break the rules of two-port network. The rules means the I1 flow in will flow out. The I2 flow in will flow out. This means the rules. For example, this network is two-port network. Assume this side as the source. This side as the source. So this current flow in must flow out. This current flow in must flow out. But if you add another branch in the outside, this branch, then there will be problem. The I1 sharp equal to I1 plus I. I1 sharp equal to I1 plus I. This will be I1. These two positions will be equal. This will be equal. But this I1 sharp will not equal to the I1. The I2 sharp will not equal to the I2. So when you add the connection out of the two-port network, the total part, this part, this part are still two-port network, but the inside, this part is not two-port network. The inside is not two-port network. It's a common four-terminal network. This is a difference. The usage of two-port network. The study method of a two-port network can be introduced to the N-port network or the multi-port network. N-port network. The complete network can be decomposed to some sub-two-port networks. When we study the terminal property, we can treat the network as black box. This means if we only care about the input and output relation, the input and the output relation, We don't care about the inside, don't care about the network inside. We can use the two-port network parameter to express. So we can treat the inside as black box. This means black box. The another method. The basic premise is we only analyze a linear two-port network. There's no independent source inside, and the initial state is 0. That means 0 initial state. We will try to find out the watch and current relation between the two ports, the left port and right port. We try to find the watch and current relation between these two ports. Equation and parameter of two-port network. Assume this is a basic premise. We only care about the linear resistor, inductor, capacitor, and mutual inductance, and the dependent source inside, but no independent source inside. The port current and the port voltage direction is assumed as this figure. This U1 positive, negative, and I1 flow from the positive to negative. The I2 flow from the U2 positive to negative. This is the basic definition of the direction, the UI direction. Pay attention. Now we have 4 variables: U1, I1, U2, I2. This is the two-terminal, two-port network. For one-port network, one port. So we have only two variables. The U and I, only two variables, U and I. But for the two-port network, we have 4 variables: I1, I2, U1, U2. So the total 6 groups parameter to describe the port voltage and current relation. We can use the U1, U2 to express I1, I2. We can also use the U2, I2 express U1, I1, or inverse. Or use I1, U2 express U1, I2, or the inverse. So we have total 6 parameters. 6 parameters. But for the one-port network, we have only 2 parameters. We use I2 express U, this is Z, or we use U2 express I, this is Y. So this for the one-port network. This for the two-port network. So the two-port network has 6 parameters, but the one-port network has only 2 parameters. Pay attention, this is a difference. Okay, let's have a rest. Rest for 10 minutes.